Fourier series. So unlike power series, power series, what do we have? Some function f of x equals to some sigma n equals 0 to infinity of some c sub n x minus x naught to the n power. Well, I mean, that generates a polynomial function centered at x naught, whatever that value is. And again, we discussed last time that such center value would give us would describe either a Taylor series or a Maclaurin series. If our center value happens to be zero, that's a Maclaurin series. If our center value x naught is not equal to zero, that's a Taylor series, right? And we can do this for nice and continuous functions. However, for functions like the ones we described at the end of the previous lecture, which are piecewise continuous functions, this Taylor series approximation doesn't work. So we have to express this in terms of a trigonometric polynomial, you know? So that's an interesting term. Well, the formal definition here is the Fourier series of a function f of x defined on the interval x going between negative L and L is given by f of x equals a naught divided by 2 plus sigma n equals 1 to infinity of some coefficient a sub n times cosine of n pi x divided by L plus another coefficient b sub n times sine of n pi x divided by L. So where a naught, a sub n, and b sub n are actually described in terms of this integral. So we need to evaluate a few integrals just to get those coefficients, unlike Taylor and Maclaurin series. Remember how we were taking multiple derivatives to get those coefficients? No, this time we're going to integrate. Well, guys, these integrals make it interesting, so to speak. All right. Well, remember last time we were discussing integrating integrating even functions and odd functions over symmetric domains. So that's something you guys might want to take advantage of because you don't want to do a lot of work that in the end is going to be worthless because it's going to give you a zero. All right. So it's important. This is what we discussed last time is very important for this. So that's because computing the Fourier series for a function f of x, again, it could be quite a process. So taking advantage of the parity of the function, if f of x, okay, if f of x is an even function, that means b sub n equals to 0. This term is going to go to 0. So our Fourier series will be simply f of x. It's going to look like this. F of x equals to a sub 0 over 2 plus sigma n equals 1 to infinity of a sub n cosine n pi x over L, right? On the other hand, if the function happens to be uh, if the function is odd here, this is odd, then a sub 0 and equal to 0 and a sub n equal to 0. And guess what? This goes to 0, that goes to 0 as well, and f of x equals simply sigma n equals 1 to infinity of a sub n, no, rather b sub n, sine n pi x over L. That is, in the case where we have an even function, we have to calculate a sub 0 and a sub n, two of the coefficients. But if we're lucky enough to have an odd function, all we have to calculate is b sub n, the coefficient of b sub n, because for odd functions, a naught equals to 0 and a sub n equals to 0. So you don't have to compute all these three integrals, which in many cases can be a tedious process. So that's why it's good to know about the parity of the function. Well, so I mean, first things first, how about we look at one example? So we're asked to find the Fourier series expansion for the function for the 2 pi periodic square wave. We usually denote it SQ for short of t, which is a piecewise function. So it's negative 1 for negative b for t being between negative pi and 0, that is the first piece, and equals to 1 if t goes between 0 and pi. And well, in this case, how do we know this is 2 pi periodic? Because between negative pi and pi, aren't there 2 pi units before the graph repeats itself? Okay, so that's something good to keep in mind. All right, well, so number one, have a look at that function. And you guys tell me, is that an even function or a not function? Hmm? It's an odd function, right? The graph. If you look at the graph, is symmetric about the origin. Okay, so this is great. So odd function, odd function. So great. A sub 0 equals to 0, and a sub n also equals to 0. So all we need here is to calculate b sub n, the only one integral here. So that means uh, the square wave function sq of t will be of the form sigma n equals 1 to infinity of b sub n sine n pi x over L, okay? Where in this case, what's L? L, do you guys agree this is simply pi? L is not a period, guys. L is actually the semi-period, if you will, because we're evaluating these integrals between negative L and positive L. So whatever period that is the value that it takes for the graph to repeat itself always divided by 2. So that's going to be L equals to pi. All right, let's get started. So here's the thing. B sub n equals to 1 over L integral between negative L and L of the function f of t sine n pi x over L with respect t. All right? So that's the function to evaluate. Okay, well, let's substitute what we have. So number one, that's what is L again? That's pi, right? That's 1 over pi. Integral between, what is that? Negative pi and pi. All right. Well, what's the function f of t? Isn't that the square wave sq of t sine n pi x over L dt? Okay. Now, okay, I know what you might be thinking. Yes, we're going to integrate negative 1 between negative pi and 0, and then another integral for the function y equals to 1 times sine n pi x over L from 0 to pi, all right? However, here is where we look at the parity of the functions. Okay, what do we have here? Okay, what do we have? Do you guys agree that this square wave is an odd function? And what about the sine function? Is that even or odd? Odd, okay? What do we get when we multiply a not function with another function? Right? Even. Okay, what does that mean? So, the integral from negative L to L of the function f of t dt will be equal to 2 times the integral from 0 to L of the function f of t. All right? Yes, because you don't want to split this into two integrals. Just multiply. I know the graph of the function is odd itself. Yes, but because we're multiplying this odd function, which is this square wave function, times the sine function, which is another odd function. Well, the end result of multiplying those two functions in the integrand happens to be an even function. Okay, so here we go. B sub n b sub n equals to the 2 times 1 over pi, the integral from 0 to pi of, okay, because we're integrating from 0 to pi, what's the portion of the graph that goes between 0 and pi? Isn't that the function 1, right? Isn't that 1 times sine n pi x over L? Well, actually, L is already pi, right? I can already substitute it. dt. Boom, that goes away. 2 over pi, 2 over pi times the integral from 0 to pi of sine n, oh, actually not nx, it's nt. Okay, I should have replaced all instants of x's with t's because we're working with t's. Okay, so let me backtrack a little bit because we don't want two variables. Okay, so that's actually t. My bad. Sorry. Okay, dt. Okay, so the integral of sine. Come on, that's negative 2 over pi cosine. Well, 1 over n cosine nt evaluated between 0 and pi. All right. Okay, so this would be equal to negative 2 over pi n pi times cosine of n pi minus cosine of n times 0. Okay, guys, what is cosine of n pi? Remember, what is it? Remember that was the alternating factor negative 1 to the n? Okay, so this will be negative 2 over n pi times negative 1 to the n. And in this case, come on, n pi. And what is cosine of n times 0? That's the same as saying cosine of 0, which is 1, right? Okay. And what do we do with this? Actually, I'm going to use the negative sign right here to reverse the order of the terms. 2 over n pi times 1 minus negative 1 to the n. All right. And that'll be the coefficient b sub n. And guys, we're ready to write the Fourier series for this square wave function. And I'm going to show you a graph of what did we do here. Okay, so again, so this square wave sq of t equals to sigma n equals 1 to infinity of 2 sub 2 over, well, actually, what is that? B sub n first times, what was that? Sine of n pi t over L, where b sub n is this number we just found over here. Okay, let me actually highlight it instead. Okay, highlight it and highlight it here. All right, so this would be equal to sigma n equals 1 to infinity of 2 over n pi times 1 minus negative 1 to the n sine of n pi t over L, which is actually pi, and this pi is reduced. So this square wave sq of t equals to sigma n equals 1 to infinity of 2 over n pi 1 minus negative 1 to the n sine times that times sine nt. And guys, this is the Fourier series representation of the square wave function we were given in the graph. And yes, you might wonder, okay, well, what's the visual of this? Yeah, that's the more that's what you guys are gonna like about this. Okay, let me okay, I already opened GeoGebra here. Let me open the file. So where is it? Square wave. Okay. So guys, this is the graph of the square wave function from 0 to pi, between negative pi and 0, 1, negative 1, 1, negative 1, and so on and so forth, right? And well, I have graphed a few of these lines to have a good representation. And also I typed a function s of x, which is the sum from n equals 1 to b, well, how many terms we want, just like I showed you the slider with the Taylor series the other day. Okay, and this is what is that? Negative 2 n over n pi. I represented it in terms of cosine of n pi minus 1. All right. Okay, let me show you this first. Okay, look at the trigonometric function. So that's the trigonometric function for n equals to 1. Actually, we have it over here. Okay, let me actually delete this one. Let me actually drag it over here. Okay, So for n equals to 1, we generate this term, guys, right here. Okay? Actually, well, cosine of phi minus what it should be computed, but for whatever reason, GeoGebra doesn't compute it. Okay? So I'm going to increase to n equals to 3. Do you see what happens? Do you see that trigonometric polynomial? What happens here? As I add more terms, b equals to 3, b equals to 5, b equals to 7, b equals to 9, and so on and so on and so forth. What happens? That series, guys, in the same way the Taylor series converges to the exponential function or to the cosine or sine function, well, this Fourier series converges to the square wave function the more terms we add. All right. So that is what we're doing here. That is what a Fourier series does. Yes. Yeah, that's something we have to talk about later. Yeah, but good question. Okay. All right. Let's have a look at the second exercise. Find the Fourier series expansion for the another 2 pi periodic triangular wave denoted T of T, uppercase T of T, which is the absolute value of T. I mean, you can see this, right? The absolute value. Let me actually highlight it instead. I mean, you guys know the absolute value. Right? However, we're making this function a periodic function, and as a result, it looks like a triangular wave. Okay. First things first. Look at the graph. Is this a function or an odd function or neither? It's even, right? Why is that even? How do you know it's even? It's symmetric to the y-axis. Correct. Okay. So let's note that first. Okay. Let's even function. So B7 equals to 0. That means we would need to calculate this time two coefficient, A sub 0 and A sub n. Okay? So, what about L? That is like the semi period. L equals to pi, right? Because we integrate between negative pi to pi. Actually, there's a little typo here on the graph that's supposed to be minus pi, not positive pi. Okay? And well, so that means because the function is even, this triangular wave T of T equals to A sub 0 over 2 plus sigma n equals 1 to infinity of A sub n cosine of n pi t over L. I know, guys, in the variable x, but for the exercises, we're using the variable t. It doesn't matter, right? These are just dummy variables. Okay. So number one, a sub 0 equals to 1 over L integral from negative L to L of the function t of t, okay, dt. But A, again, isn't that function an even function? Again, so that means we can do 2 times 1 over L, which is 1 over pi, times the integral from 0 to pi of t of t. Okay, guys, here is the thing. What's the function that we're going to input in the integrand? Check this out. This function right here, do you guys agree this is the function f of t equals to t, where t goes between 0 and pi? All right, it's just a diagonal line passing through the origin. This other line right here is f of t equals to negative t because of the negative slope with t going between negative pi and 0. Okay? So you have two options. You can integrate twice negative t between negative pi and 0, or integrate 2 times t between 0 and pi. I like the second version because I don't want to deal with negative exponents. And even if with negative numbers, I mean, not exponent. And even if we use if we use the other form, it's not going to be any harder. I just want to go with positive one. So that means I'm going to integrate t dt that equals 2 over pi, 2 over pi, integral from 0. Oh, actually, we can integrate t squared over 2 from 0 to pi. Cancel out the 2's. That equals 1 over pi. That's pi squared minus 0 squared. That is actually reduces to simply pi. All right. So that's the coefficient of a sub 0. That's it. Okay. All right, guys. What about the coefficient a? So you might want to put a check on a sub 0. Now, what about a sub n? Okay, so here is where we need to look for the formulas. What's a sub n? Go back to page 3. A sub n, 1 over L, integral from negative L to L of the function, in this case f of t, not f of x, cosine of n pi x over L, or t rather, with respect to t in our exercise. All right. Okay, so that's the cosine one this time. So now, uh, so a sub n equals to 1 over L, first of all, integral from negative L to positive L of the triangular wave t of t, cosine, okay, of n pi t over L dt. But again, guys, before substituting anything, because I mean that domain negative L to positive L, we need to think about it first. So what about the parity of g of t? Isn't that again an even function? What about the parity of the cosine function? Isn't that another even function? So what is it? Even times even. What is that equal to? Even, right? Okay, so that means we can evaluate this integral as a 2 times the 1 over pi, the integral from 0 to L, which in this case is pi. And well, since we're integrating, guys, between 0 and pi, this t of t, this uppercase t of t, which denotes the triangular wave, will be replaced with f of t equals to lowercase t, because we're using the positive side of the graph, right? You guys following me here? Okay, so that'll be t cosine of n pi t over L, which is pi again, dt, which is, what is that equal to? That reduces to 2 over pi, integral from 0 to pi of t cosine n t dt. How do we evaluate that integral? Integration by part. And guys, at this point, I'll let you use the tabular method. That's because since we're going to do a bunch of integration by parts here. I mean, using that as a not necessarily shortcut, well, that could work, of course. Okay, so when we use the tabular method here, so let's set up the tabular method for this. Well, in this case, we need to decide which function do we differentiate, which function do we integrate. Which one is it? Which one is which? The t will get differentiated. So let's set u in this case, right? Let me use a different color for this. So u, which is the function to be differentiated, that's t. The derivative is 1. The derivative of 1 is 0. And now, until you get to 0, you stop with the process. Well, that means the dv will be to integrate the cosine function. Well, what's the integral of the cosine function? Isn't that a sine of nt times 1 over n? All right. Oh, wait a minute. No, that should be the first integral, not here. Okay, so that goes down here. So cosine nt. And then what's the integral of sine nt times 1 over n? Isn't that negative 1 over n squared cosine of nt? All right. Okay, guys, how do we use the tabular method? Again, the first row, so we need to alternate signs over here. So that's always plus, negative, plus. If we had more rows, plus, minus, plus, minus, plus, plus, minus, I mean, plus, minus, plus, etc. And what do we do? Multiply this diagonally, and well, for the next diagonal, which is 0 times whatever we would have gotten of the third integral, well, that's 0, right? So that's why we stopped there. Okay, so this would be careful. Don't forget about this 2 over pi. So 2 divided by pi times whatever we get from integrating that by parts, which is positive times a positive, that's t over n, t over n, sine of n, t. Negative times a negative, be careful, that's positive, 1 over n squared cosine of nt. And then evaluate this between 0 and pi. All right? Let me continue. Let me continue down here with the process because it's not going to fit in the same line. So this would be equal to, okay, I'm going to use a bunch of grouping symbols here. Okay, so that's 2 over pi, curly braces, brackets for the evaluation at the upper limit of pi. That'll be t, which is pi, pi over n, sine of n pi, plus 1 over n squared cosine of n pi, right? So that's the evaluation of the upper limit. The evaluation of the lower limit, that'll be minus 0 over n sine n times 0 plus 1 over n squared cosine of n times 0. Okay, so that's the end of the evaluation. Okay, a lot of it's going to be simplified here. So how about, okay, check sine of n pi. Okay, sine of all the multiples of pi, like sine of pi, sine of 2 pi, sine of 3 pi. What is that equal to? That goes, all this term goes to 0. Cosine of n pi. Remember the alternating factor? Well, we'll talk about that one in a second. Okay. What's next? Sine of n times 0. That's essentially sine of 0, and then on top of that, multiply by 0. I mean, that's gonna be 0. Cosine of n times 0, which is cosine of 0. Only the cosine goes to 1. All right. Not the whole term. Okay, so what is left in here? So we will be left with 2 over pi again, 2 over pi. I'm going to open brackets for this. That is pi over n times 0. Oh, that's actually 0. 1 over n squared. But what did we say about this cosine of n pi? Didn't we say this is negative 1 to the n? All right. Minus, what is that? Simply 1 over n squared. 1 over n squared. Okay? So let me do the following, guys. This will be, I'm going to take the n squared, which is a common factor in the denominators here, and multiply across with pi right here. So that is 2 over n squared pi times negative 1 to the n minus 1. And we're done obtaining the second Fourier coefficient, that is a sub n. And guys, we're ready to write the Fourier series for the triangular wave function. Okay, so that is coming back, t of t equals to a sub 0 over 2 plus sigma n equals 1 to infinity of a sub n cosine of n pi t over L, which is what's a sub 0? What did we get for a sub 0? Didn't we get pi? So that's just going to be pi over 2. Wait. Oh, yeah, pi over 2 plus sigma n equals 1 to infinity of a sub n, which is all this madness here. So let me highlight. Let me highlight. This is all we're going to substitute in place of a sub n. Okay, that is 2 over n squared pi times negative 1 to the n minus 1 times cosine of n pi t over pi. All right. Well, there's really not much to simplify other than dividing out those pi's right here. So that'll be pi over 2 plus sigma n equals 1 to infinity of 2 over n squared pi negative 1 to the n minus 1 cosine of nt. final answer. So this is the Fourier representation of this triangular wave. And just like I showed you a graphic representation for the previous exercise, well, it's not going to be an exception for this one. Okay, so let me go back to GeoGebra here. Let me open the file, triangular wave or triangle wave. Let me open the file. All right, so here we have a nice triangle wave. Okay, so here I have this function s of x that which represents the Fourier series we calculated by hand, which is pi over 2 plus the sum of 2 over n squared cosine of n pi minus 1. In this case, I went back to cosine n pi. I could have done negative 1 to the n. It doesn't matter when you do this in GeoGebra. Okay, and I'm going to go from n equals to 1 to as many terms as we want. How do we do that? Well, by playing with the slider. Now, guys, I would like you to observe this triangle wave. I mean, unlike the square wave, doesn't that function looks more like a wave than the previous case and the case before? I mean, because let me do this. So, I mean, that's the function for s of x equals expanded the n equals 1 for n equals to 1. I'm going to play with the slider here. I'm going to do n equals to 3. Do you see how in this case we don't see these waves right here like we saw in the previous exercise? That's because, I mean, we don't require too many terms to have this Fourier series to converge to the actual value of the function, isn't it? So this converges more rapidly than the other case because of the shape of the wave in this case that we're dealing with, right? So that can happen every once in a while. Okay, so let's do one more exercise. Okay, find the Fourier series expansion for the 2 pi periodic function. Actually, this is not supposed to be s sub q. This is supposed to be simply some f of x. Okay, let me actually fix this real quick. Okay, so this is just some function f of t. It's not a square wave. All right. So what do we have for this function actually? Well, we have a function whose value is equal to 0 in the interval negative pi to 0, as stated in the piecewise function. Also, we can see the graphic representation. And then we have a diagonal line y equals to t between 0 and pi. The question here is that function even? Is that function odd? It's a neither, right? Neither. So that means, in a way, we're screwed. We'll have to calculate the three coefficients, a sub 0, a sub n, and b sub n. It's not like the other cases in which some of them were 0 because of the parity of the function. So, all right. So, let's see. So, neither, even, nor odd. Right? So yeah, let's get started with a sub 0, which is, oh, by the way, what's the period? Isn't that again? Okay, we said it says 2 pi, right? So that means L will be the semi period, which is again going to be pi. All right. So that'll be 1 over L integral from negative L to L of the function f of t dt. Okay, that is 1 over. Okay, check this out. 1 over pi. In this case, guys, the function is neither even nor odd. We cannot multiply the integral by 2 and then evaluate from 0 to pi. So in this case, because also this is a piecewise function, we need to evaluate one, we need to set up one integral for each of the pieces in the piecewise function. So that'll be, on the one hand, the integral from negative pi to 0. But what's the function to integrate? Isn't that f of t equals to 0? So of 0 dt plus the integral from 0 to pi of what's the function to integrate? Isn't that t dt? Well, yes. I mean, in a way, we're still integrating in the end from 0 to pi, but not because of the same reason as before, because of the evenness or of the function, right? So but still. So this is equal to 0. All right. That equals, so a sub 0 equals to 1 over pi times the integral from 0 to pi of t dt, which is 1 over pi times t squared over 2, okay, from 0 to pi. That is 1 over 2 pi in the denominator, okay? So that is pi squared minus 0 squared again, which reduces nicely to pi over 2. Well, let me do it here, pi over 2, all right? So it's the first coefficient. No, change my mind. A sub 0 equals pi over 2. So that's our first coefficient. 3. Okay, let's have a look at the other two coefficients, a sub n and b sub n. Okay, so number one, a sub n equals 1 over L, the integral from negative L to L of the function f of t cosine of n pi t over L dt. And guys, unfortunately, in this case, we're not going to be able to use it to multiply by 2 and integrate from 0 to pi. Well, we will again, but again, not for that same reason. Okay, so this is what we do. So number one, let me substitute 1 over L integral from negative L to L f of, or rather, let me do from, no, negative 1 over pi from negative, okay, from negative pi to pi of f of t. Okay, let me call it f of t for now, cosine of n pi t over pi dt. Okay, so in this case, because of the nature of the function f of t, it's neither even nor odd. I would need to set up two integrals. So 1 over pi, I'm going to open brackets. So that's going to be the integral between negative pi and 0. And again, that's going to be the 0 function multiplying the cosine function, cosine of n, boom, nt dt plus the integral from 0 to pi of what function are we integrating between 0 and pi? Do you guys agree? Is the function simply t times the cosine of nt dt. Okay? Well, actually, the first we can call it a day for the first integral, all right? At least for this integral, because it's got to be 0, because 0 times cosine in the integrand is 0. The integral of 0 from a number to another number is going to be naturally 0. Okay? So we are left with the following. A sub n, okay? A sub n equals to 1 over pi times the integral from 0 to pi of t cosine nt dt. Okay? But guys, didn't we actually got this result? Didn't we already evaluate the same integral in the previous exercise? Okay, so I'm just going to copy the result from the previous exercise. That is 1 over pi times, what did we get for the integral right here? We got 1 over n squared, okay, times negative 1 to the n minus 1 over n squared, okay? And let me note that we got this from example number 2, all right? That's where I'm getting it from. Okay, so this will be, okay, then equal to, again, me factor out the n squared, so that equals 1 over n squared pi times negative pi, I mean negative 1 to the n minus 1. Okay, so that's a sub n. At least we saved some work using a result from the previous exercise. All right. So now we need to calculate one more, b sub n. Okay, that's going to be the interesting one to do. All right, so b sub n, can we actually kind of box this? Okay, so b sub n, which in this case equals uh 1 over L in general, integral from negative L to L of the function f of t sine this time of n pi over n pi t over L dt. That equals 1 over pi integral from negative pi to, well, actually, should I? Yeah, I mean, let me actually break this up into the integral from negative pi to 0, but isn't that for the function 0 times sine of n pi t over pi dt plus the integral from 0 to pi of, what is that? T sine n pi t over pi dt. Okay? And again, guys, we have freedom here because 0 times sine is 0. The integral of 0 from a number to another number, 0 here. The whole thing is going to go to 0. Okay? So let me simplify the integral, the remaining integral, and then set up the problem. Okay, so that's going to leave us with the following. 1 over pi, b sub n, equals 1 over pi times the integral from 0 to pi of t. This time it's a sine. Cancel out the pi's. Sine of nt dt. Okay? How do we evaluate this integral? Again, integration by parts. And guys, again, I'm going to use the tabular method for this one. Okay? So, so in this case, the function to be differentiated, it's the t function, t. The derivative is 1, the second derivative is 0, and we stop there. dv, which is the function to be integrated, that is sine of nt, the integral of sine, that's negative cosine of nt, but actually I need to multiply by 1 over n. And then the integral of cosine, which is positive sine times the negative 1 over n, that's going to be negative 1 over n, but squared, sine nt. Okay? All right, guys, make sure to alternate signs plus, minus, plus, and then multiply diagonally, multiply diagonally. As soon as you get to the 0, that's where you stop doing the diagonals. Okay, so careful with the signs this time. What do we have? Positive times a negative, right? That is negative, so that is number 1. Okay, I'm going to do 1 over pi. I'm gonna open curly braces. That's wait a minute. No, let me do brackets first. So that's times whatever we get from the result using integration by parts. So that is negative t over n cosine of nt. And then negative times a negative equals to positive 1 over n squared sine nt. And we will evaluate all of this between 0 and pi. How about that? All right. Just like we did in the previous example, let's do the same. Upper limit minus lower limit. Yes, we have a lot of letters going on, but it works the same. So 1 over pi. Oh, here I'm going to go curly braces. So that is open brackets for the evaluation on the upper limit. That is, be careful with signs. That is negative pi over n cosine of n pi plus 1 over n squared sine of n pi, close brackets, and subtract the evaluation at the lower limit 0. That is negative, okay, be careful, minus negative 0 over n cosine of n times 0, okay, what is plus 1 over n squared sine of n times 0. Close parentheses for the angle, close brackets for the evaluation, and close curly braces for the entire multiplication with 1 over n at the very end. Okay? Simplify. Simplify. Okay. Sine of multiples of pi. What is that? What was that again? 0. Okay, the whole term is going to go to 0. cosine of 0 equals to 1 times 0 over n, which is 0. That's the whole thing is going to go to 0. And then sine of n times 0, which is sine of 0. That's actually also another 0. Good. Okay, so we're left with the following. That is 1 over pi times bracket negative pi over n cosine of n pi. But what's cosine of n pi? Remember, what is that equal to? Negative 1 to the n, all right? Okay, now, we have an interesting situation here because, okay, what is that? Okay, the pi's are going to go away. Do you guys agree with that? Okay, have the pi's go away, and that's going to leave us with positive times a negative. That's going to be negative 1 over n, okay, times negative 1 to the n. But guys, this is not simplified. We need to simplify this to lowest terms. How? Okay, this negative multiplying with the 1, isn't that the same as saying negative 1 in parentheses? And multiply this with negative 1 to the n, everything divided by n. And because we have the same base, what do we do with the exponents? Plus 1. So that'll be negative 1 to the n plus 1 over n. We're almost done. All right. We're almost done. Okay, so now let's go ahead this time and write the Fourier series. But because this function happened to be neither even nor odd, we're going to have a complete Fourier series f of t equals to a sub 0 over 2 plus sigma n equals 0 to, oh, wait, n equals 1 to infinity of a sub n cosine n pi t over L plus b sub n sine of n pi t over L. So that is going to be our Fourier series. We already have a sub 0, a sub n, and b sub n. Let's just substitute and call it a day for the series. Okay? So that equals f of t equals to, what was a sub 0? It wasn't that pi over 2, right? But what is pi over 2 divided by 2? Isn't that equal to pi over 4? Okay, plus sigma n equals 1 to infinity. Okay, what was a sub n again? A sub n. Okay, this big madness here, right? 1 over n squared pi times negative 1 to the n minus 1. Okay, so let me write it down. That is, you do curly braces for this one. I'll have to do it. 1 over n squared pi times bracket negative 1 to the n minus 1. Then I'm gonna do more compact in a way, right? With lesser grouping symbols. That times cosine of n pi t over pi, which is L, plus b sub n, which is what we just found, negative 1 to the n plus 1 over n, okay? That times sine n pi t over pi, that's curly braces here, okay? Well, to avoid writing too many grouping symbols, I'm going to have this negative 1 to the n minus 1 to multiply with the 1 right here. So that'll be f of t equals to pi over 4 plus sigma n equals 1 to infinity of bracket negative 1 to the n minus 1 over n squared pi cosine n pi, or rather nt rather, plus what's next? Negative 1 to the n plus 1 over n sine of nt. We're not done yet. We need to box our final answer, right? Yes. All right. Oh, of course. No, no, no. We're not done yet because you want to see a picture of this, right? Of course. Okay. So how does that look like? Okay. I call it a ramp wave. I didn't have a name for it. I'm pretty sure there's a name for this kind of wave, you know? So, all right. So that's what the what the function looks like, with multiple repetitions. Again, here I have the sum pi over 4 plus a negative 1 sum plus sigma negative 1 to the n minus 1 over n squared pi times cosine of n x. In this case, I use x because GeoGebra uses the variable x, right? And then plus negative 1 to the n plus 1 over n sine of nx, where n goes between 1 and b. What's b? The upper limit, which will be the number of terms we add to the series. Actually, we already have computed for n equals to 1. I'm going to actually that looks like, a number plus some coefficient cosine plus another coefficient times sine. That should look like a sine wave, like this way. Well, let's add more terms and see what happens. Check this out. Oh, wait, it gets twisted and kind of adapts to the shape of the piecewise periodic function, right? Let me add more terms. And do you see how that converges to the graph of the piecewise and periodic function, the more terms that we add. Of course, we don't want to compute all of this by hand. You would need at least like 5 pages or so. All right. So, and that was a Fourier series for this function. And actually, that was the end of the section. Okay.